Have you ever wondered how computers understand language? The answer lies in the fascinating field of formal languages. These are not languages like English or Spanish that we humans use, but rather sets of strings constructed over a defined alphabet. Picture an alphabet as a finite set of symbols, the building blocks, if you will. Now, a string is simply a sequence of these symbols. Together, they form the basis of a formal language. These languages are the focus of study in theoretical computer science and mathematics. They provide a structured way for us to communicate with machines, and for machines to communicate with each other. It's like a secret code, a language that only computers can truly understand. So when we talk about how computers understand language, we're really talking about formal languages. But how do we construct these languages, you might wonder? The answer lies in the basic building blocks of formal languages: alphabets and strings. Let's start with alphabets. In the context of formal languages, an alphabet isn't a list of letters like A, B, C. Instead, think of it as a finite set of symbols. These symbols could be anything: numbers, letters, special characters, emojis, you name it. Now let's move on to strings. A string is a series of symbols chosen from an alphabet. It's like constructing a sentence using the words from a specific language. For instance, if your alphabet is made up of the symbols 0 and 1, then 0101 and 110 are strings over this alphabet. So what's the takeaway here? These symbols and strings are the building blocks of our formal languages. They provide the foundation upon which we construct and understand the complex languages of computer science. So what exactly is a formal language? Well, in the grand scheme of theoretical computer science and mathematics, it's a bit like a secret code. Imagine you've got a box of building blocks. Each block has a symbol on it. These blocks are your alphabet, your finite set of symbols. You can put these blocks together in any way you like to create a string, a sequence of symbols. Now, a formal language is a collection of these strings, all built from the same set of blocks or the same alphabet. But there's a twist. Not just any string can be a part of a formal language. The strings that belong to a formal language must follow specific rules or patterns. Like a secret code, each string in a formal language conveys a specific meaning, a specific piece of information. In the world of automata theory, formal languages take on a life of their own. They become the DNA of computational systems, the core structure that underpins everything from your smartphone apps to the algorithms that power the internet. Regular languages, context-free languages, context-sensitive languages, recursively enumerable languages. They're all types of formal languages, each with their own unique properties and applications. Formal languages are the conduits through which we communicate with machines, and through which machines communicate with each other. They are the medium through which we express algorithms, the means by which we define and manipulate data structures, and the language we use to describe the behavior of computational systems. If you've ever written a line of code, then you've worked with a formal language. Every programming language, from Python to JavaScript, is a formal language. And if you've ever passed a sentence in English or solved a mathematical equation, then you've worked with a formal language too. In essence, a formal language is a way of organizing and categorizing strings of symbols. It's a way of translating our ideas into a form that machines can understand, and it's a way of making sense of the complex world of computation. Let's dive deeper into the types of formal languages. In the realm of formal languages, regular languages occupy a special place. They're like the fundamental particles, the building blocks upon which more sophisticated languages flourish. But what exactly is a regular language? A regular language is a formal language that can be recognized by a finite automaton. Now that's quite a mouthful, isn't it? Let's break it down. A finite automaton, also known as a state machine, is a mathematical model of computation. It's a mechanism that can be in one of a finite number of states at any given time. It reads in a string of symbols, and based on the current state and the symbol it's reading, it transitions to another state. If after reading the entire string, the automaton ends up in a designated accept state, it's said to recognize that string. Now, a regular language is simply the set of all strings that a given finite automaton recognizes. It's like a club, and the finite automaton is the bouncer deciding who gets in and who doesn't. Regular languages can also be generated by something called a regular expression, a concept that many of you may be familiar with from programming. A regular expression is a sequence of characters that forms a search pattern. primarily for use in pattern matching with strings, or string matching operations such as find or find and replace. In the grand hierarchy of formal languages, regular languages are the simplest class. They're less expressive than their more complex counterparts like context-free or context-sensitive languages, meaning they can't represent as many different kinds of structures or patterns. But that simplicity is also their strength. Algorithms for processing regular languages are generally more efficient, and their theoretical properties are better understood. So regular languages, with their elegant simplicity and efficient processing, serve as the foundation for the study of more complex languages in formal language theory. They're the first step on a journey into the fascinating world of automata, grammars, and languages. Regular languages are the foundation upon which more complex languages are built. But there's more to formal languages than just regular languages. Let's delve into the realm of context-free languages, which are a step up in complexity from regular languages. These languages can be generated by what we call a context-free grammar. Imagine a language where you can make rules about structure, but these rules don't depend on what's happening elsewhere in the sentence. That's a context-free language in a nutshell. They're like the independent adventurers of the language world, not caring what's happening around them. Context-free languages are incredibly useful in computer science, particularly in the world of programming languages. They provide the underpinning for many of the syntax rules that programmers follow when writing code. If you've ever written a for loop or defined a function, you've been working within the rules of a context-free language. But what if we need to express something a bit more complex? That's where context-sensitive languages come in. Unlike their context-free siblings, these languages allow rules that do depend on their surrounding context. Think of them as the diplomats of the language world, always aware of their surroundings and adapting their behavior accordingly. Context-sensitive languages are more expressive than context-free languages, allowing us to describe and model more intricate systems and processes. They have applications in some more advanced areas of natural language processing and formal language theory. For example, they can help us understand and parse language nuances that are dependent on context, such as pronoun resolution or idiomatic expressions. It's important to note that while these languages offer a higher degree of expressiveness, they also come with increased complexity. But this complexity is what makes them so powerful and versatile in different applications. From programming languages to natural language processing, context-free and context-sensitive languages provide us with the tools to express detailed and nuanced ideas. Context-free and context-sensitive languages allow us to express more complex ideas and structures. Finally, let's talk about the most general class of formal languages. Yes, you've guessed it right. We're diving into the deep end with recursively enumerable languages. These are the languages that can be recognized by a Turing machine, the theoretical construct that's the foundation of all modern computing. You see, a Turing machine, named after the brilliant mathematician Alan Turing, is a mathematical model of computation that defines an abstract machine, capable of manipulating symbols on a strip of tape according to a table of rules. It's like the supercomputer of formal languages, flexible and powerful, with the ability to simulate the logic of any computer algorithm. Now, when we say that a language is recursively enumerable, we mean that there's a Turing machine which will accept any string that is in the language. If a string isn't in the language, the Turing machine could either reject it or run forever. That's the catch. It doesn't have to halt for strings not in the language. From another perspective, recursively enumerable languages can be thought of as the languages that a Turing machine can list out, given enough time. So, if you had a Turing machine and infinite time on your hands, you could get it to generate all the strings in a recursively enumerable language. The beauty of recursively enumerable languages is that they include all computable languages. In other words, if there's a problem that a computer can solve, then the set of all possible solutions to that problem is a recursively enumerable language. To put it succinctly, recursively enumerable languages represent the full potential of what we can express with formal languages. They're the most expressive, the most inclusive, and the most general class of formal languages. They encompass everything from the simplest regular languages to the more complex context-sensitive languages. So as we delve into the fascinating world of theoretical computer science and explore the intricacies of formal languages, it's the concept of recursively enumerable languages that truly showcases the boundless possibilities of computation. Recursively enumerable languages represent the full potential of what we can express with formal languages.